Hey guys, welcome back to my channel, Math Sprint, and you are watching the second video of my calculus crash course. Today I'm going to be explaining differentiation and its fundamental rules. Before we begin, I think you need to make sure that you're familiar with at least these concepts because they're going to be very important if you want to understand this chapter in calculus. So first understand these concepts and then continue with this video. The topics to know are algebra, quadratic equations, straight line graphs, how to plot a graph on a Cartesian plane, polynomials, permutations and combinations, the binomial theorem, basic set notation, exponents and logarithms, functions, limits, and continuity. If you want to understand functions, limits, and continuity, you can also check out my first video on calculus, which covers these topics. And also note that I'm only working with real numbers and not imaginary numbers in this video as well. First, the gradient of a tangent. A tangent is a line that touches the plane curve exactly once and only once. So let's take the graph on the left as an example to explain this. The red curve has the equation y is equal to f of x. The blue line is tangent to the red curve at point F, which has the coordinates a, comma, f of a. The h is the difference between the x coordinates of points F and M. M is at the top over here. Now suppose point M were to move along the red curve and close to point F, which also lies along the red curve. The green line over here, which connects points F and M, would keep on getting shorter and shorter as the value of h would get extremely small and approach zero from the right. Eventually, as h approaches zero, again, h is the difference in the x coordinates of F and M. So as h approaches zero, the gradient of Fm, this green line here, will approach the gradient of the tangent at F, that is the blue line here. So the green line's gradient will become nearly equal to the gradient of the blue line as the x difference between points in F and M approaches zero. So therefore, we can say, using limits, that the gradient of the tangent at point F is equal to the limit of f of a plus h minus f of a divided by h as h approaches zero. Now we come to the derivative function. The derivative function is a function that essentially outputs the gradient of the tangent to a function at a particular point. This is not the exact definition, but I think for your understanding, it can be described as this. If the function is labeled as f, then the derivative function is labeled as f dash. You can think of it like adding an apostrophe over the function, but in mathematics, never call it an apostrophe. I'm only calling it for your understanding. We'd refer to it as a dash. So f dash. F dash of a is the value of the gradient of the tangent to y is equal to f of x at the point where x is equal to a. So f dash of x is equal to the limit of f of x plus h minus f of x divided by h as h approaches zero, as you can see from this limit notation here. F dash of x represents the derivative function. So if we're given y in terms of x, then y dash or dy by dx are commonly used to represent the derivative. Now do note this, dy by dx is not a fraction. When we use it in math, it may appear like a fraction, but it is not an actual fraction. Dy by dx is just the derivative of y with respect to x. Now over here, we have delta y is used to represent the change in the value of y, and delta x is used to represent the change in x. So note here that this symbol over here, right next to x, if you can see my mouse here, that is just the lowercase form of this delta. This capital delta, and this is lowercase delta. This notation was originally used by the German mathematician Gottfried Leibniz, just for your information. So delta y by delta x represents the average change in y for every unit change in x. So therefore, we can derive this by saying f dash of x is equal to the limit of delta y by delta x as delta x approaches zero. So that's equal to dy by dx. And additionally, for a specific point, we denote it like this. F dash of a is equal to dy by dx for x at x is equal to a. Differentiation. So differentiation is the process of finding a derivative function, also known as the gradient function. So given a function f of x, we obtain f dash of x by differentiating it with respect to x. So let's take this example below here. We have the function 2x cubed plus 4x plus 3. So the gradient function would be dy by dx, which is 6x squared plus 4. Now, I'll explain the rules of differentiation soon. Just understand that this entire branch of mathematics, where one has to find the derivative function, is called differentiation. Now, let's move on to the rules of differentiation. So here's some basic differentiation rules. I'll summarize them for you. The first one, differentiating any real constant yields zero. The second one, differentiation of function multiplied by the constant yields the derivative function multiplied by the same unchanged constant. And the third one, differentiating the sum of two functions gives the sum of their respective derivative functions. All right, so let's talk about the major rules of differentiation. Now, rule number one, differentiating x to the power of n gets n times x to the power of n minus 1. So let's solve from some problems over here. The first one, y is equal to x cubed. Now let's apply this first rule. The 3 becomes the coefficient of the derivative function, and 3 minus 1 is equal to 2. So the new degree of x becomes 2. So we finally get dy by dx, which is equal to 3x squared. Now the second one, y is equal to 4x to the power of 5. So what we do is that we get dy by dx. Oh, actually, by the way, if you're confused by how I solved it, don't worry. The problem actually goes into a bit of differentiation rule too, which I'll explain as well. So if you recall one of the basic differentiation rules that I explained just a minute ago, you will realize that this problem requires us to apply two rules actually. The first rule is that the constant will remain unchanged. The function next to it will be differentiated. This means that if we take the 4 out and differentiate x to the power of 5, we have to multiply 5 and 4 to get 20. So therefore, the derivative function is 20x to the power of 4. So the third one. Now here's a challenging one. Y is equal to x squared plus 2x plus 1. This also goes a bit, again, into differentiation rule 2. Again, don't worry, I'm going to explain it later. Here we have to apply technically 3 rules in total. First, we have to differentiate the individual functions in the summation. And that is x squared, 2x, and 1. The derivative of x squared is 2x, the derivative of 2x is 2, and the derivative of 1 is just 0. So if you add all of these derivative functions, you'll eventually get 2x plus 2 as your derivative function. So dy by dx is equal to 2x plus 2, as I've simplified it here. So now here's the proof of the first major rule of differentiation. I felt like including this proof in the video because this proof is very similar to the proofs of other major differentiation rules. So it's important to just understand this general logic, so maybe you can prove other rules yourselves. Okay, we start with we get the function f of x is equal to x to the power of n for all real values of n. So therefore, f dash of x, using the formula that I explained before for the gradient of a tangent at a particular point, f dash of x is equal to the limit of f of x plus h minus f of x divided by h as h approaches 0. So we start with this. And since f of x plus h is equal to x plus h whole to the power of n, we get this by just plugging in x plus h into the function. So now we are going to use the binomial theorem. Simplify the binomial expansion of x plus h to the power of n. You can notice that when you cancel out the x to the power of n on the left side of the numerator and on the right side of the numerator. So over here you have x to the power of n, and over here you have x to the power of n. You cancel these two and you just get the remainder of the binomial. After that, you can just take out the h because all of the terms in the numerator are divisible by h. The h in the numerator and the h in the denominator cancel out because we know they're not 0. H approaches 0, but does not equal 0. Remember that fundamental difference. So it's perfectly allowed for us to cancel out h from numerator and denominator. So further simplifying all of these terms in the expansion, you now have to plug in h is equal to 0 into this whole thing basically. And finally, you're left with n times x to the power of n minus 1. And this is the derivative function for f of x is equal to x to the power of n. All right, so now we're at the second rule of differentiation. Now this is very useful in differentiation, and I think it's perhaps the most important rule to know when doing it. The chain rule is useful because it involves simplifying complicated equations. Essentially, if you have a function whose input is another function, then the derivative of the entire function with respect to x is the derivative of the outermost function with respect to the intermediary function u, multiplied by the derivative of the intermediary function u with respect to x. So if that seems a bit complicated, I'll make it easier to understand. You know how I mentioned earlier that dy by dx is not a fraction? Well, let's pretend like it was one. Then by this logic, the du of the denominator here, this can be canceled out by the du in the numerator here. So if you cancel these two out, you'll be left with dy by dx. So you can think of it as like separating a fraction into the product of two fractions. Now, that's not how it's supposed to be. You shouldn't describe it like that mathematically. I'm just helping it make it easier for you to understand. So here's some practice problems below. Now, the first one, y is equal to 3 over 2x minus 2. So the equation becomes y is equal to 3 times u to the power of minus 1. And here we're taking u as an intermediary function, 2x minus 2. So we're using the first major rule of differentiation. dy by du is equal to the minus 3 u to the power of minus 2. Also, we have to find du by dx. And using the previous rule, which I explained, du by dx is just equal to 2. Multiplying du by dx with dy by du to get dy by dx, we find that dy by dx is 2 times minus 3 u to the power of minus 2. So this gets us minus 6 over u squared. So if you substitute u back with 2x minus 2, you'll get minus 6 over 2x minus 2 whole square. Now, here's another one. Y is equal to the square root of 7x minus 1. Now, I think it's important to know that the square root of a number is basically raising that number to the power of 1 by 2. So just remember that it's an important thing to understand here. So let u be equal to 7x minus 1. So we're following the same steps here. dy by du is equal to half of u to the power of minus half. And du by dx is equal to 7. So dy by dx, since it's equal to dy by du multiplied by du by dx, we get 7 by 2 u to the power of minus half. Now again, substituting u back with 7x minus 1, we get dy by dx is equal to 7 by 2 times 1 over the square root of 7x minus 1. Now the third one last problem. Y is equal to the x squared minus 4, the whole thing to the power of 5. So let u be equal to x squared minus 4. So y is equal to u to the power of 5, basically. Now dy by du would just be 5u to the power of 4. And also, we can calculate du by dx by saying du by dx is equal to 2x. We get this by just differentiating x squared minus 4. So multiplying these two different derivative functions together, we get dy by dx is equal to 2x times 5u to the power of 4, which is 10x u to the power of 4. Now substituting u back with x squared minus 4, you get dy by dx is equal to 10x times x squared minus 4 to the power of 4, the whole thing to the power of 4. All right, so differentiation rule 3, the product rule. If f of x is equal to u of x v of x, then f dash of x is equal to u dash of x v of x plus v dash of x u of x. This is a formula that you basically need to by heart. As you keep practicing problems, you won't even need to rely on it anymore as a template. You can just recall it from like basic instinct practically. So an example, y is equal to x times the square root of 2x minus 3. We can see that we need to use the product rule right now because there are two smaller functions within a larger one. The first is x and the second is the square root of 2x minus 3. See here, what we do is that dy by dx will be equal to the square root of 2x minus 3 multiplied by d by dx of x plus x multiplied by d by dx of the square root of 2x minus 3. So eventually, as you keep simplifying that continuously, you'll eventually get 3x minus 3 divided by the square root of 2x minus 3. Now, differentiation rule number 4. So if f of x is equal to u of x by v of x, that is to say f of x is the quotient of two functions, then f dash of x is equal to u dash of x multiplied by v of x minus v dash of x times u of x, the whole thing divided by v of x whole square. Pay attention to the fact that the denominator is v of x whole square and not v dash and not the square of v dash of x. I've seen a lot of students make these kind of mistakes and it can cost them a lot. So make sure the denominator is v of x whole square. So here's an example on the bottom right that we can solve. Y is equal to the 2x squared minus 3, the whole thing divided by x. So here we can just essentially consider these two to be two functions. So u of x is equal to 2x squared minus 3 and v of x is equal to x. So if we do differentiation on the numerator and denominator, the u dash of x will be equal to 4x and v dash of x will be equal to 1, as per both as per differentiation rule number 1. So if we just use this formula and plug in all of the values for u dash of x, v of x, v dash of x, and ux, we'll eventually simplify it. We'll get dy by dx is equal to 2x squared plus 3, the whole thing divided by x squared. So differentiation rule number 5. If f of x is equal to a to the power of x, where a is some constant, a real constant that is, then f dash of x is equal to f dash of 0 times a to the power of x. That is to say, it's equal to a to the power of x ln a. Now, if you say a is equal to e, that is the natural exponent e, and f of x is equal to e to the power of x, then we can say f dash of x is equal to e to the power of x using this very same rule. So here's some sample problems that we could do right now. So y is equal to e to the power of 5x squared. So let's differentiate 5x squared first using rule number 1. We get 10x. So the result is dy by dx is equal to e to the power of 5x squared, then using the chain rule, multiplied by 10x. And that gets us 10x e to the power of 5x squared. Now the second one, y is equal to k to the power of 5x plus 1, where k is a constant. So we differentiate 5x plus 1 and get 5. So then using the chain rule again, we get dy by dx is equal to k to the power of 5x plus 1 multiplied by ln k multiplied by the derivative of 5x plus 1, which we already proved to be 5. So that the whole thing is that the derivative function is 5e to the power of 5x plus 1 ln k, where k is a constant, a real constant. All right, so differentiation rule number 6, the rule for logarithmic functions. So if f of x is equal to ln x, then f dash of x is equal to 1 by x. Then if we include the chain rule in this, then if f of x is equal to ln of g of x, where g of x is some function, then f dash of x is equal to g dash of x divided by g of x. So let's do some problems right now. Y is equal to ln of x squared. So what we get is that we get dy by dx is equal to 1 by x squared first, because we have to, because as you can see from this formula, we take the function inside the logarithm at the bottom. And then we do the chain rule where the derivative of x squared is 2x. Multiply those two together and you get 2 by x. Now, actually, there's a way to do this without using the chain rule. If you know the laws of logarithms, you can see it. So we take the 2 over here and we put it in front of the logarithm, because if you know the laws of logarithms, that means if you do ln of the square of a number, then you can take the number 2 and put it here. And essentially that means y can be simplified to 2 times ln x. And if we do the differentiation on that, we get 2 by x. It's pretty simple. So the second one, y is equal to ln of x cubed plus 2x squared. So dy by dx will be equal to 1 over x cubed plus 2x squared multiplied by the derivative of the function inside the logarithm, x cubed plus 2x squared. So after simplifying that, where the derivative of x cubed plus 2x squared is equal to 3x squared plus 4x, we simplify that and we eventually get 3x. dy by dx is equal to 3x squared plus 4x, the whole thing divided by x cubed plus 2x squared. Actually, you can cancel out the x from the numerator and denominator if you want to simplify it further, but either way, the answer is still the same. So now the third one, y is equal to ln of x by 2x plus 3. So let's let g of x be equal to x by 2x plus 3. So to find g dash of x, we need to use the quotient rule. The function in the numerator can be labeled as u of x, which is equal to 2x plus 3, and the function in the denominator can be labeled as v of x, where v of x is equal to x. So v dash of x will be equal to 1. So we just substitute as per the formula and we get g dash of x is equal to 3 by 2x plus 3 whole square. And yeah, after simplifying. So now we use the chain rule. We multiply g dash of x with 1 over g of x. And finally, we get dy by dx is equal to 3 by x times 2x plus 3, after canceling the 2x plus 3 from the numerator and denominator over here. So this means that actually this derivative function we've derived by assuming that x is not equal to minus 3 by 2. So keep that in mind. Now, differentiation rule number 7, the rule for trigonometric functions. This is the last rule that I'm going to be dealing with for this video. I think these two tables are a bit self-explanatory. The trigonometric functions in the left table are in terms of x, and the trigonometric functions on the right table are in terms of another function f of x. So here the chain rule is applied when differentiating with the trigonometric functions in terms of another function. Okay, so here's something interesting, a challenge problem. See if you guys could do this yourselves. Pause the video right now and try it. Here's a hint. Make this large function in terms of smaller functions. So I'll just give you some time, a few seconds. All right, so here's the answer. I'll explain how to do this problem. Let's create 3 functions in total. Let f of x be equal to x squared plus 2x plus 1. Let g of x be equal to sine of x squared plus 2x plus 1. That is sine of f of x. And let's let h of x be equal to tan, essentially h of x is equal to y. So, and that after substituting g of x into this equation, you get h of x is equal to tan of g of x. So then we find the derivative functions for each of them. F dash of x is equal to 2x plus 2. G dash of x is equal to cos of f of x times f dash of x. And if you substitute these values, you get 2x plus 2 times cos of f of x. Then h dash of x, you get sec square of g of x times g dash of x. So you just keep simplifying and substituting the values for g of x, f of x, f dash of x, and g dash of x. And you'll eventually get h dash of x is equal to sec square of sine x squared plus 2x plus 1 times 2x plus 2 times cos x squared plus 2x plus 1. So if you got it right, give yourself a big pat on the back. This was not an easy question for a person who's never done calculus before. But if you didn't get this question right, don't worry, you're still new to calculus. Practice makes perfect. Small increments and approximations. Earlier, I stated that dy by dx is equal to the limit of delta y by delta x as delta x approaches 0. So therefore, it follows that for very small values of delta x and delta y, dy by dx is approximately equal to delta y by delta x. So take a look at the diagram on the right. Delta y is the change in the value of y, and delta x is the change in x. If we were to make delta y and delta x incredibly small, say about like 0.01 or 0.02, for example, the exact amount of how small can vary, but it usually is a real number that's close to 0. Then if you notice, delta y by delta x will nearly equal dy by dx at this particular point. Delta y by delta x is a fraction, unlike dy by dx, because it is a ratio between the net change in y and the net change in x. But there's one very important understanding you should have. dy by dx, or the derivative function, is the rate of change of y with respect to x for a specific value of x. But delta y by delta x is the average rate of change of y with respect to x for some particular domain. Very rarely do they ever equal each other. So understand this difference because it will be very fundamental in my next video on applications of differentiation. Problems involving approximations. So let's do one problem. A graph has the equation y is equal to x squared plus 2. Approximate the change in y if x increases from 1.0 to 1.00 plus h, where h is small. You can take your time to solve this problem, so I recommend that you just pause this video for some time. Okay, so time's up. Here's the answer. I'll explain this. We have the equation y is equal to x squared plus 2. We differentiate it to get the derivative function dy by dx, which is 2x. At x is equal to 1.00, the derivative dy by dx is equal to 2 times 1.00, which is 2.00. Now, delta x, since it's the final value of x minus the initial value of x, delta x is equal to h. As I mentioned before, delta y by delta x is a fraction. So that means that you can take the delta x here and multiply it by dy by dx to approximate the value of delta y. So after substituting the values that we obtained over here, we can eventually conclude that delta y is approximately equal to 2.00 h, where h is a very small number. Okay, the next question. A graph of the function f of x is equal to x squared exists. If the value of x decreases from 1.02 to 1.01, approximate f of 1.01 using Euler's method. For this problem, just ignore the mention of Euler's method right now. I'll get to that in the next video of applications of differentiation. Just pause the video and work on this problem. Okay, time's up. Here's the answer. So f of x is equal to x squared. So the derivative function is f dash of x, which is 2x. F of 1.02, when we substitute 1.02 into the function, we get 1.02 whole square, which is 1.0404 precisely. And f dash of 1.02 is equal to 2 times 1.02, which is 2.04. So since we know, again, delta x is equal to the final value of x minus the initial value of x, delta x is equal to minus 0.01. And again, we're using the same principle of how delta y by delta x is a fraction, so we can take the delta x here. And after that, we find dy by dx for x is equal to 1.02. We already did find it, so that's 2.04. Substitute the values, and you get delta y is approximately equal to minus 0.0204. Now, since delta y is the final value of y minus the initial value of y, we can approximate it to become minus 0.204. Now, after that, now our goal is to find f of 1.01. We already know f of 1.02 from over here. It's 1.0404. So after that, we do 1.0404, taking it to the right side of the equation, minus 0.0204. And that gives us f of 1.01 is approximately equal to 1.0200. So I just want you to know that the actual value and the approximated value have a difference of just 0.0001 units for y. So actually, if we were just to plug in if we were just to plug in 1.01 into the function f, then we would get 1.01 whole square, which is 1.0201. You can see the enormously small difference between the approximated value and the actual value. So this method of approximation can yield values that are very close to the actual values. Okay, so we're almost done with this video, guys. Just some important concepts to clarify. Second derivatives. F dash of x is called the first derivative, but it's possible to take a derivative of a derivative to obtain f double dash of x. So you just perform differentiation on the derivative function to obtain the second derivative. I'll take you to a problem and you can do the actual differentiation. We have f of x is equal to e to the power of x sine x. So first we use the product rule to obtain f dash of x. And we can get sine x times e to the power of x plus e to the power of x cos x. Now, considering that technically these two we can just divide this as the sum of two functions. So we can say f of x is equal to g of x plus h of x. G of x is equal to e to the power of x sine x. And h of x would be equal to e to the power of x cos x. So if we were just to find the derivative functions of g to the power of g of x and h of x, we get f double dash of x is equal to g dash of x plus h dash of x. And we do the product rule on each of them, and we eventually get f double dash of x is equal to essentially e to the power of x sine x plus e to the power of x cos x, plus e to the power of x cos x minus e to the power of x sine x. Now I've used square brackets over here so you can just draw some parallels. Which parts of the function, which parts of f double dash of x were taken from doing differentiation on this part of the function, and which parts were taken from this part of the function. So eventually, after simplification and after canceling e to the power of x sine x from here and here, we eventually get f double dash of x is equal to 2e to the power of x cos x. Okay, so you should understand that if there exists a second derivative, then what we can do is we can just keep performing differentiation endlessly on a function. That means there also exists third derivatives, fourth derivatives, fifth derivatives, sixth derivatives, and so on. They all exist. These are called the higher order derivatives. I put a general formula for your understanding, d of n plus 1y divided by, sorry, the derivative d n plus 1y over dxn plus 1, sorry, this is a bit difficult to say, is equal to the derivative of dny with respect to x. So essentially, from the third, also note one more thing, from the third derivative onwards, we no longer use the apostrophe to denote a higher order derivative. Instead, we just denote it with a number enclosed by parenthesis, as you can see over here. So basically, f of fn dash x is the nth order derivative of the function. So if you see over here, we've put a 3. That means f dash of f dash of f dash of x. If this were a 4 instead, we'd have 4 f dashes instead of 3. So that's higher order derivatives for you. All right, thank you guys. That'll be the end of this video. Make sure you hit the like and subscribe buttons to see my future videos on mathematics. Until then, stay tuned.